Okay, so let's get started. Today we have the pleasure to have Fabian Koehlinger. So Fabian is a PhD student at Leiden Observatory. He's working on cosmology and large-scale structure by means of weak gravitational lensing. He's a member of the KIDS collaboration. And today he's going to talk about cosmological constraints from weak lensing, present measurements, and future challenges.
Thanks for the introduction. So exactly, let me just walk you quickly through the talk. So I'll give a very short introduction on what weak lensing actually is, or or gravitational lensing in general. And hopefully at the end of the introduction it becomes clear what I mean with cosmic shear and galaxy-galaxy lensing, because those will be the two major analyses that I will present during the talk. And finally, I'll leave you with conclusions, of course. Okay, so let's start. Just a brief snapshot of what is cosmology in 2015. So from the CMB, here a pretty picture of Planck CMB, and also galaxy clustering probes. We have a pretty good picture about what the cosmological model should be, and the big term that always comes up is lambda CDM. And you can basically fit all sorts of different cosmological probes with only 6 parameters as a minimal set. And the big question, though, is like, what is the physical nature of especially 2 of these parameters, namely dark matter and dark energy? So these 2 are the holy grails at the moment in cosmology, because we have pretty names for them, but we don't really understand on a physical basis what those are. And that's basically the driving source behind cosmology at the moment. So why should we use gravitational lensing? I hope it comes out for you in the back, but I'm not sure. So let me just explain that with a short analogy. Let's imagine you want to measure population density on Earth, and as a tracer for that, you decide to use the light emitted during night. So this is a picture of the Earth at night, and you see basically all the big metropoles. Here the US East Coast and also parts of Canada are probably mapped out. Japan is a bright spot. And based on this picture, you might also conclude that actually the Netherlands seems to be a super highly populated country, which is true with respect to its size, but definitely the light emission is way too much in terms of the actual number of people living in the Netherlands. So what I want to convey with this picture is basically we have cosmological probes, and many of those use basically the light emission of galaxies as a tracer to actually map out the underlying total matter distribution in order to get hold of dark matter especially. But when you use these tracers, you get a biased picture. We know, well, we expect that, and you can actually also learn a lot of astrophysics from the bias parameter. But actually, if you're really interested in the total matter distribution, I would argue that gravitational lensing has the advantage that it's an unbiased probe. So it doesn't depend on the physical nature of the matter, and it's really tracing all the matter and not just a biased parameter following the whole matter distribution. So that's a main motivation for why gravitational lensing, and in particular weak gravitational lensing, is a valid method for cosmological inference. So what is gravitational lensing in a nutshell? So we usually have a source in the background. We have some lens in the foreground. Here it's taken to be a very massive lens, named a galaxy cluster. So the largest assemblies of mass that we find in the universe at the moment. And what happens to light from this background source due to the foreground lens is actually a GR effect, right? Light follows geodesics, and due to the mass of this foreground lens, actually space-time is distorted. So when light of this background source follows the geodesics, what we actually receive on Earth are sometimes even multiple images, like indicated with these orange lines here. That's then the regime of strong gravitational lensing. And what this looks like in actuality is shown in this picture. So this is a famous galaxy cluster, Abell 370. And it's especially famous because you see this really weird object right here. But that's actually just what I've shown in the previous slide. It's just a very highly distorted background galaxy, right? And due to the mass of the whole galaxy cluster in the foreground, actually the light is so distorted that, that you have really these weird shapes. But this is the regime of strong gravitational lensing, and strong evidently because, well, it's really distorting images. You can also see some other arcs right here. So this is slightly less prominent. And what I'm going to talk about, though, will be weak gravitational lensing. And the term weak makes sense because we can't actually see weak gravitational lensing just by eye. So it's a statistical approach. And what you have to do is basically you measure the shapes of thousands or millions of these tiny background galaxies. And when you average over enough of them, you will actually see that there is a coherent imprinted feature on the shape on these galaxies, which is due to the gravitational shear caused by the foreground lens. So it's really a statistical approach because, of course, galaxies have intrinsic shapes, right? We know galaxy evolution is really complicated and you can end up with a lot of different objects. But if we average over enough of them, in the presence of a lens, we will still find a coherent feature which is just due to gravitational lensing. And that's what we are after. So once you've measured enough shapes, you can actually apply two different kinds of statistics. What I've shown so far is basically the correlation of shear and position. So you take a massive lens, here again the galaxy cluster, but it can also be a galaxy group or even just a single very massive galaxy. And then you just average azimuthally around this object. And what you do by that is really you build up a correlation between the shear and the position of the object. And that is also termed galaxy-galaxy lensing. So this will be one part of the talk later on. But then really interesting for the major cosmological parameter inference is the shear-shear correlation. And if you correlate shear at some position here and shear at some position over there, what you are basically mapping out is the whole matter distribution in between, right? So you're collapsing the whole line of sight matter distribution basically into your lensing analysis. And it's very obvious that this is really a good cosmological tool if you have all systematics under control, of course. And you could also imagine, instead of just looking at one plane, you can actually slice up this whole plane, right? And then you also get a hold on the whole structure evolution between you and the furthest and the background source the furthest away. And for all these reasons, this is also termed cosmic shear because it's really tracing the overall matter distribution. Okay. So especially weak gravitational lensing is at the moment in a golden age. So we are right here in terms of time. So in the Netherlands and Europe in general, we are very busy working on KITS, the kilo degree survey. But at the same time in Japan and Princeton mainly, HSC is going on with Subaru. And of course the big thing in North America and especially in the US is DES, the dark energy survey. And you see, we are talking here about thousands of square degrees, which is the area of these weak lensing surveys. And another parameter that you should take care of is basically the number density of the background galaxies you will be able to resolve. But a word of warning here, so these numbers are just very rough indications. It's because they really depend on your shape measurement method. And different collaborations use different definitions, so don't take them at face value, just as a word of warning and as a rough idea of what these surveys will yield. And then the last parameter, which is interesting in this context, is actually the median redshift of your galaxy distribution, because that basically tells you what is the leverage you have on cosmological inference. Because the further away your source background distribution is, the more line of sight you you have in between, and yeah, the better that is for cosmological inference. And actually, all these 3 surveys going on at the moment are actually pathfinders, in a sense, for the next stage of weak lensing surveys in Europe. Very famous Euclid will be a space-based telescope, especially designed for gravitational lensing, weak gravitational lensing. And here we are really speaking of order half the sky as area for the survey. And then again, North America is very busy in developing LSST at the moment, a ground-based survey, but also mapping basically half of the sky in total. But here we are speaking on much further away timescales, so there's still a lot of development going on. Okay, so from this slide,
the half sky
yes.
for Euclid, that's both hemispheres presumably, and they're just cutting out zones of void.
So it's 15,000 square degrees in total. I'm not sure if they split it between hemispheres or if it's enough if you just take one hemisphere. So.
What is the overlap with LSST?
Actually, the overlap will be substantial because LSST is slightly larger still in design than Euclid. But actually, at the moment, there are discussions going on about actually buying LSST bands in order to also get photometric redshift estimates. Because Euclid is only a one-band space telescope, and it really needs other bands in order to infer photometric redshifts. So there's some crosstalk between the 2 collaborations, yeah, about redshifts especially. Okay, so basically from this slide, I basically tell you weak lensing is in its golden age right now, so you should all become weak lensers. But that is only one side of the medal, because weak lensing is also facing a lot of challenges. And one of these challenges is really getting accurate photometric redshifts. So a lot of the community was really busy working on getting ever better shape measurement algorithms. And now it turns out that also actually getting accurate photometric redshifts is paramount for your cosmological analysis. Because if you misestimate your photometric redshifts and you introduce a bias, that is important. It's really about a bias. That is basically shifting the whole power of your power spectrum that you're interested in the end. So you should better make sure that your photometric redshifts are really accurate. The second point, as always in weak lensing, is shape noise. This is a very famous sequence by Preidel et al. From 2009. So we start with an intrinsically shaped galaxy right over here. We add gravitational shear. You see there's a preferential direction now imprinted on the shape. Then usually we have an atmosphere, except for Euclid, which really blurs the whole image. Our detector is pixelized, so we lose another bit of information during that process. And of course, well, the detector is also noisy, so we also get noise right here. So what we are trying to do is basically estimating an accurate and precise shape from things like that. And that is technically very difficult, of course. But in order to beat down this term, this noise term, actually that's the whole motivation why weak lensing surveys become ever larger, because once you just make your survey bigger, so wider and deeper preferentially, you beat down this noise term just because it scales with 1/n of your objects. So that is basically the motivation behind why weak gravitational lensing becomes larger and larger in terms of survey area. But once you go deeper, especially, you run into another problem, which is actually blending. So you have naturally just sources that overlap, not necessarily physically, but just because, well, you can always find something in the background of another object, right? And if you don't want to lose these objects, you should better make sure that your shape measurement algorithms especially can separate these objects still reliably. So this is also, a big field of research going on right now in all the collaborations, how to deal with that. And especially HSC will run into difficulties with that because they go to substantially deeper redshifts. Okay, so those were the challenges in general. Now let me switch to the first analysis of the talk, which is based on cosmic shear. So it's based on measurements. And if you really want to dive into all the details, there's a paper on the archive. Feel free to check it out. And just as a reminder, or as an introduction to the lensing of large-scale structure, so what we are talking about is basically the weak lensing power spectrum, CL. And we have two indices right here, which basically run over redshift slices. And let's ignore all the prefactors. What is really important about this thing are these two terms here, the geometry and the physics. So you have some ratio of scaling functions and distances. And those account for your redshift distribution in the source sample and basically the whole lensing geometry, so the distance between you and the lens, between you and the source background, and then between lens and source. So the whole technicalities of lensing go into this term. And then the juicy part about this power spectrum is really that it's basically an integral over the ordinary 3D meta power spectrum. Right? And that is really the thing we are after, especially with cosmic shear, to infer the physics of the meta power spectrum, which is the meta power spectrum of the density fluctuations, right, imprinted in the meta distribution today. Okay, then very briefly, how do we measure that? So I said already we have to correlate shapes. So what you do is you take a nice field of view, you measure all the shapes, and then you just build up correlation functions by relating the shape over here with every other shape in the field, right? And the straightforward way to go is always use a correlation function, because that's just simply multiplying scalar numbers and taking care of distances and angles. But you've seen already the theory is actually formulated in terms of a power spectrum or power spectra if we talk in terms of redshifts. So what I want to argue is basically that we should also try to focus especially on this part and measure it directly from the data instead of basically taking these real space measurements and convolving them back into, we take the real space measurements usually and then we take the theory and basically convolve it back into real space estimates. But I want to make the point that instead of doing that, we can also try to just measure the power spectra directly from the data. Okay, so speaking of data, I'm not applying this technique yet to any of the ongoing surveys, but basically, another famous survey, and which is still state of the art at the moment, it's CFHT Lens. Also, Canada was actively involved during that project, which is actually the C in the acronym. And what you find is basically these are 4 discontinuous fields on the sky, variably sized. So this is roughly 5 by 5 degrees. This is roughly 7 by 8 degrees. So you see it's inhomogeneous, but well, that's what you have to live with. A very good feature about this survey is all the data is public. And by data, I don't only mean the images, but really the shear catalogs are public. So you can really just go download and play with that, which is quite nice. In terms of area, if you add everything up and then subtract these white patches, because those failed very essential tests for systematics, you get something like 100 square degrees of total area. This is, of course, really tiny in comparison to other cosmological probes at the moment. For your information, I will split the survey actually into 2 redshift slices. They are rather broad. So the low redshift slice goes from 0.5 to 0.85, and then the high redshift slice goes from 0.85 to 1.3. And the reason for that, for the experts, I don't want to open this Pandora's box, but it's basically to minimize the effect of intrinsic alignments. So for this analysis, it suffices to say that really, by splitting the data into just these 2 very broad redshift slices, you're basically minimizing these effects, and they're negligible, especially given the error bars of the data in the end. Okay, so the goal of the analysis, as I said before, is really that I want to extract the lensing power spectrum and not just measure correlation functions and then take the whole theory and multiply that with really nasty Bessel functions and so on. But I want to extract lensing power spectra. I want to go out to large scales so that I'm basically coupling to the linear cosmology, which is also not really what has been done yet in the CFHE lens analysis. And yeah, you should always do it tomographically, right? Because that just gives you greater leverage on the cosmological inference. The reasons for doing that is exactly you have better handling of the scale mixing when you talk with your theory in L space and also with your measurements in L space, right? That's exactly what I said. Well, if we talk in correlation functions, I basically have to take the theory, convolve it with Bessel functions, and then I'm really mixing scales, which is usually okay if you're interested in several parameters, but if you're interested in parameters that really leave distinct features in L space, for example, you're washing out that information to some degree. So that's one of the reasons. Then once you're talking in power spectrum language, it's really straightforward to just couple that directly to CMB likelihood analyses and so on. So that's just a very nice technical feature. And yeah, as I said, the scale-dependent features, right? And here I'm really talking about neutrinos. We all know by now that they have mass. And of course, baryon feedback, which is also a hot topic right now in the literature.
Where's the likelihood,
Yeah.
especially with the complex region it's dealing with? You have to fully characterize the likelihood of certainties, whether you're dealing with a correlation function or a power spectrum. So it isn't like one is simpler than the other.
No, that's correct. True.
I mean, for some purposes, sometimes with CMB, it does make sense because there isn't that much correlation L to L. But here, there's a lot.
Yeah, I agree. Okay, so what do these features look like? So if we just look at the first panel, that's really a ratio of 3D power spectra. So I take modified power spectra with respect to some reference model. And in blue, you basically see the effect of AGN feedback, which turned out to be one of the more realistic cases for baryon feedback that came out of these old simulations by Shea et al. Done in Leiden. And in red, you see an exaggerated effect of 3 degenerate massive neutrinos. And by exaggerated, I mean, well, the mass, I assume, is very high. It's 0.18 eV. We know already that the mass is probably lower than that. But just to make clear what the effect is. So, okay, you see the AGN feedback basically leaves really this distinct feature I was talking about. So it's really a dip in K-space. And then the neutrinos basically, yeah, if you average a little, I mean, it's really basically a constant shift in power, right? So you're lowering the amplitude. And then, of course, you have to take this meta power spectrum and integrate it over your lensing kernel, which in this arrow is supposed to be, of course, tailored to the CFHE lens analysis. And you start already to wash out some of the features in L space, nevertheless, right? So you basically see the AGN feedback only becomes measurable at high L's, right? So L of 500, 600-ish. And then the massive neutrinos, again, cause a constant shift in power. But again, that is exaggerated. It's probably, well, the lower the mass of the neutrinos, the smaller the effect is, right? So we're really after some 5 to at most 10% effect in amplitude shift, right? So it's challenging to do that. Yeah, then finally I can show you the measurements, really. So what I've taken then, instead of correlation functions, is actually a quadratic estimator method based on Hu and White, who already thought about this in 2001. And we expanded just the notation to also include tomographic bins so that we actually end up with an autocorrelation of the low redshift bin in blue, the autocorrelation of the high redshift bin in red, and the cross correlation in between. And the solid line in each panel, that's actually the best fitting power spectrum coming from a likelihood analysis. And then, just for your information, so what I'm showing here is really the information of all 4 fields, basically averaged with inverse variance weights just to make nice pictures. In the likelihood analysis, I treat every CFHE lens field independently. And a whole lot of work actually went into estimating these error bars, because we didn't just trust the Fisher matrices that come right out of the algorithm, but we really decided to basically use of the order of 200 independent mock realizations of CFHE lens data to really get run-to-run estimates on the error bars. And that's really just some considerable amount of runtime that you have to spend. Okay, for the cosmological analysis, I should mention that I'm only taking the 4 bands in this white window in each panel, because I have a very good reason to exclude the lowest band and also the second to last and last band. So this comes out of a systematics analysis, and for that reason we decided to be conservative and exclude these bands. Although we lose some information, of course, by doing that. Okay, so the surprising result of every weak lensing analysis at the moment is the well-known lensing banana. We're talking here in the parameter plane of the total matter density, omega m, and sigma h, which is related to the amplitude of your power spectrum. So those 2 parameters are actually the parameters the most constrained by weak lensing, just because it's the most sensitive to those 2. What I show here is a simple lambda CDM model in blue, 1 sigma and 2 sigma contours, and then what I would call, as a trained physicist, the most reliable model, actually the lambda CDM plus all. And all here means I leave a free amplitude for the baryon feedback. I include a free parameter for the total mass of neutrinos, and 2 nuisance parameters for photometric redshift bias. And yeah, you see that the contours are also much broader in comparison to the simple lambda CDM estimate. And then just for reference, Planck CMB only 2015 analysis are these 2 tiny contours here. But again, let me remind you, CFHE lens is much less than 1% of area on the sky, whereas Planck is whole sky. And of course, the redshift leverage is very different for the 2 surveys, right? So it's natural to expect that weak lensing at this moment is not really compatible. Just to give you an idea of the full posterior, so don't focus too much on all these, but it's basically to address the point of massive neutrinos, which is shown in this panel here. So this is lensing only, and if I take that as a constraint, I would constrain the total neutrino mass to be less than 4.5 EV at 95% credibility, which of course is not competitive to any CMB result, because we know already by Planck alone that it's below 0.8, and if we add in some other probes like BAOs, we know it's below 0.2 for sure. But that is basically just, that was for me at least the motivation, like trying to trace massive neutrinos. I knew that CFHE lens would probably be very challenging to see anything at all, but I wanted to build up the machinery, basically thinking of kits and other ongoing surveys. Okay, then a short comparison with other literature values. So again, in this 2-parameter plane, omega m and sigma 8, the main analysis of CFHE lens was probably Heyman's et al. 2013. It used correlation functions, 6 tomographic bins, and if you translate the real space bins basically into L space, they start somewhere at L of 500, whereas my analysis starts at an L of 80. So I really go out to large scales in comparison. And then, again, the 1 sigma constraint from Planck in between, right? And just conveniently, yeah, my analysis is somewhere right in between the CFHE lens and it also touches Planck by a bit. So it's relieving some of the tension that was already claimed to be there in the literature between CFHE lens and Planck. Just.
Have you identified why the result
Yeah, that's actually something we really want to look into much more detail, so we haven't done it for that analysis yet, because it's very hard to compare the real space correlation function analysis with the power spectrum analysis in terms of what is the information content of each bin and so on. But I would guess one point probably relieving the tension is really that I go out to much larger scales, because then you're really in the regime of this linear power spectrum almost, right? So that
I think it's somehow associated with the nonlinear direction.
it could be related to that, yeah, because
So one thing you could do,
yeah.
I don't know if this would be any good because maybe the data is not strong enough, but you could actually, even though there aren't very many bands, you could effectively take the correlation function information and compress it onto L space by an expansion.
Yeah.
You know, and then that would at least tell you what it, at some level, what it's trying to do in terms of L space.
Yeah.
Have you gone for that?
We haven't really thought of that yet, but I think we definitely should.
It's an interesting way of
Yeah.
doing, of trying to translate their space into your space.
Yeah, I mean, it's really not trivial because of all the nasty Bessel functions and so on. But I think,
It's not bad, right? Because you've got, in both cases, you're dealing with trying to mimic broadband power.
yeah,
So fast oscillations are always damaging.
yeah, okay, that's true. Yeah, I agree. We should definitely look into much more detail into that, and especially in ongoing surveys, I would argue.
It would be useful for the community because,
Yeah.
as you rightly point out, myself being a Planckian, this was pretty egregious, this shift, and of course it has impact on things like dark energy.
Yeah.
So
Yeah.
I wouldn't say I'm happy because if there's tension and the tension is real, that's neat too. But it's interesting that you're moving in the direction towards the Planck result.
Yeah, I agree. We should definitely look into much more detail into that.
Can I ask one other question? Sorry.
Yeah.
So the CMB lensing from Planck, is there an equivalent sigma 8 over gamma figure?
I did that at some point in my analysis where I really took the whole constraint from Planck CMB plus lensing. And then basically what happens is that this whole thing moves more into direction of the lensing.
Well, I was thinking of just the lensing by itself, the CMB lensing by itself.
Ah, okay. No, I didn't look at this figure in particular.
Tension of the CMB lensing in Planck.
Okay. Yeah, I'll definitely have a look at that. Okay, just for convenience, you can basically extract this degenerate contour into just a 1D projection of parameters, right? So that is done here. It's called S8 now in DES terminology, and it's just a product of sigma 8 times omega m to the power of a half divided by some normalization. I mean, that's just a trick basically to project a constraint perpendicular to this line of degeneracy, right? That's all that happens in this plot. And this is widely quoted in the literature, whereas it's hard to always find the 2D constraints. So just to give you an idea, so again, Planck CMB only is this gray band over here. And then the latest DES result is this arrow bar, this previous CFHT lens analysis by Koehlinger. Over here, they didn't use any tomography. The Heyman's result again right here. And then, as you see, I've not only tried the lambda CDM plus all and lambda CDM, but everything in between, basically, right? So just relaxing one parameter at a time and then building up more complicated models. And now you should all basically ask, so which model is then actually the one that I should trust out of this analysis? And you can actually give a very quantitative answer to that when you use evidences. So the likelihood analysis code that I used is MontyPython, just some advertising for that. It's pretty neat. And you can also use multinest as a sampler, and that basically allows you also to get evidences right out of your analysis. And then So the logarithm of the evidence is shown in this column. And then you can construct something called the base factor, which is just a ratio of this logarithmic evidence. And yeah, you can calculate that over here. And minus sign is always bad for the more complicated model because it means there's no preference over the simplest model. So the only model out of all of these which has slight preference but really just barely worth a mention is the one which includes only the nuisance parameters for photometric bias. So a long story short, the simplest lambda CDM model is actually the one that that describes the data already the best. So there's no need for any extra parameter, at least not in CFHT lens. Last but not least, you can then of course also combine Planck CMB only plus shear. Planck only 1 and 2 sigma are in red over here. And then once you fold in also the shear analysis, you get the blue contours. And as you see, you break the degeneracy between omega m and sigma 8. And at face value, you also decrease the Planck alone error bars by a tiny bit. Okay, that concludes basically the first section. The next section then will focus now on galaxy-galaxy lensing. Again, there's a paper if you're interested in the details. But before I come to that, I have to tell a very brief story about cluster counts. So cluster counts is another nice tool for cosmological inference. All you have to do is basically count the most massive objects in the universe, construct a function out of that, and you will also get cosmological constraints out of that because every cosmological model basically predicts how many objects at which redshift of which mass you should find. Right? So that's a powerful tool, and it was also used extensively in the Planck analysis. So here you see just, for example, number count functions now only plotted as a function of redshift, just to give you an idea what this looks like. And the most surprising result maybe from Planck in 2013 was then that actually the cluster counts don't really agree with the primary CMB results, again plotted in this omega m sigma 8 plane, right? So you see there's, yeah, people call it tension. I'm not sure if it's really that strong of a tension, but again, it triggered a lot of discussion in the literature. And what Planck used for cluster counts is actually the Sunyaev-Seldovich effect, right? Because that you basically get almost for free from your observations. And the tricky part about that is you have to relate the strength of this Sunyaev-Seldovich effect to some mass, right? You need some mapping between the strength of the signal and the actual mass of the cluster. And that is actually a point addressed here. So what we talk about then is something like scaling relations, right? So you have to relate this mass to the Sunyaev-Seldovich effect. And what Planck used in the 2013 analysis was basically X-ray cluster estimates, right? And they were based on simplifying assumptions like every cluster is relaxed and in hydrodynamic equilibrium and so on and so forth. But we know that by doing that, you introduce a bias because we can compare, for example, to hydrodynamic simulations. And what people believe to be a realistic prior on the bias between the Sunyaev-Seldovich mass and the true X-ray mass is something of the order of 20% or plotted as 1 minus b 0.8, right? So that was assumed to be believed to be the bias that you would expect. But then actually they went through the exercise of leaving this parameter free and then combining the CMB plus the SC cluster counts. And then you find in order to reconcile both data sets, you actually have to assume a 1 minus bias of 0.6, which is really large, especially compared to expectations of what people thought the bias should be. And one way out of this situation is, again, hopefully weak lensing, because here I show a plot by Hoekstra. So he's really plotting weak lensing masses on the y-axis and Planck estimates of masses based on the Sunyaev-Seldovich and X-ray scaling. on the x-axis. And actually here, the purplish, I don't know which color that actually is, that's the second set. So Henk used the CCCP, Canadian Cluster Comparison Project, which he still performed here right at CITA. And another group called Weighing the Giants, that's this other color here. And we're still talking about small numbers. So Planck cluster counts is using something like 150 to 180 clusters, I believe. And actually the overlap between these Planck clusters and both weak lensing probes is of the order of maybe 30 overlapping clusters in both data sets. But what you can use then is really the weak lensing mass as a tracer for the scaling relation, right? And then you see again in this plane what this yields. So Henk's CCCP bias is exactly on top of what people believe should be the bias, so it's 0.8. And then Weighing the Giants, though, is going slightly more into direction of reconciling CMB and SZ cluster counts. So the message being there's still a lot of work to be done in order to find the optimal combination of that. And people actually in the field now have the hope that really once you solve the last remaining systematics and weak lensing, that weak lensing actually is the better mass scale probe for doing these cluster counts in the future. So just to give you an idea, so this is the 2013 Planck analysis, right, this tension. And then in 2015, they used different priors. So primary CMB is the dashed contours right here. And then if you believe Weighing the Giants, there is basically no tension at all any longer. And if you believe CCCP, though, there's still some tension, but still it's not, maybe not as severe as it was in 2013. So weak lensing can clearly help in resolving that. And the long goal motivation for that is really a projection plot, again by Planck 2015. So they assume if you could really point down the mass bias to an error bar on the order of 1%, if you would then already combine the CMB and SZ cluster counts, you can basically map out the whole distribution for the total neutrino mass, which would be a very cool measurement to do, right? And that with data already taken now, just by resolving this mass bias issue. Okay, so that is basically the context for my analysis. So my analysis is basically a prediction paper for Euclid. So I assume Euclid has already taken the data for half of the sky. And as a byproduct, you will also get a lot of shear just for galaxy clusters, right? So the idea is that you use these large area weak lensing surveys then as a gauging probe for these mass scales in order to do cluster counts. One thing you should get right, though, in order to get accurate and precise mass estimates from weak lensing is then that there's also cosmic shear, right? So a lot of line of sight projections actually which contribute to the error. So just shown here is the perfect NFW, where basically no other noise is assumed. And then here's a realistic picture of a galaxy cluster. That's what the shear looks like in data. And the difference then just in this probability plot is basically the dashed curves that only accounts for shape measurement noise in weak lensing, just for 3 clusters at different mass. And then once you fold in basically all the line of sight, large-scale structure noise, you end up with much broader contours just to establish the correct estimate of errors. You can kind of propagate that into a figure of merit in a sense. So again, this is the mass of clusters, and then I assume a stacked analysis of all the Euclid clusters that are to be found, and basically express the error on the mass estimate as sigma. And then I just scale it by the total number of clusters in that mass bin. And then different colors, again, are different redshifts. And dashed is, again, just taking shape noise into account. And solid is basically folding also this large-scale structure noise. And basically what I want to convey with this picture is the statistical errors expected by a Euclid cluster survey are just yeah, impressive, because this gray line over here, that's the very ambitious goal of achieving the multiplicative bias for Euclid, right? I mean, it's really talking a lot about future, and it's a very ambitious goal, but basically what this shows is that your statistical error is almost only limited by this fundamental systematic limit, right? So the message, statistical uncertainties will be very low for a Euclid-like cluster mass survey. But once you're in this statistical regime, you have to carry about systematic errors, of course. And what I've looked at in particular is an effect introduced by cluster members that are scattered into your background source sample just by basically misidentifying the photometric redshift, right? That will happen because photometric redshift algorithms introduce, yeah, at best only some error, but at worst also catastrophic outliers, and that might, in the worst case, yield cluster members that carry no lensing signal at all, but you mistake them as background galaxies, and basically the shift in the lensing efficiency between the two leads to an overestimate of cluster mass if you have this effect going on. But you can correct for that. I just want to make the point you should account for that, definitely. Another famous systematic effect is miscentring, because for your weak lensing analysis, you always have to assume a mass center of your cluster. And observationally, that's sometimes very ambiguous, what the true center of the cluster is. And if you misestimate the center of the cluster, again, just focus on the blue lines, which is the shear. So the perfect NFW prediction is this solid line. And then I assume you really misestimate the center, and you get this estimate here. So you see the discrepancy is really on the inner scales of the cluster. And again, that leads to an overestimation of the true cluster mass. So you should also correct for that. But it's straightforward to describe that statistically, right? You can construct a distribution of miscentered clusters, for example, which has a certain width. So you have two parameters that you can marginalize over in an analysis, which is done in this picture. So the reference is the dashed blue curve. And then I assume I have no prior information at all on these miscentering parameters. And that indeed yields a bias in mass, right? Which is the red solid curve. But that is a very, very conservative estimate, because already now there's data available, for example, from X-ray probes that can be used to construct really more realistic priors on the miscentering distribution in particular. And once you take this prior information into account, you can perfectly account for this effect, right? So bias is gone, and it's definitely solvable. So the point I want to make is really that Euclid, especially in combination with probes like eROSITA, which is a large X-ray survey, also producing a cluster count survey, basically are really very promising probes in order to solve this problem and maybe to lead one day to really a strong estimate of the total neutrino mass. Okay, so since I'm slightly running out of time, I think I'll just leave up the conclusions right there, and thank you all very much for your attention. Thanks.
So, eROSITA, it's great, but many of the objects won't have that, a very large number of photons. So exactly how would eROSITA be used for enhancing the outcome of these big optical surveys?
Well, the idea there was especially basically that with X-ray data, you have much better control over this miscentring, right? Because you can always basically estimate the X-ray center of the cluster and then take that as an estimator for the true cluster center. And then it's easy to compare that to the optical center of your cluster and then really construct this distribution of miscentering from data. So that is the idea behind why I mentioned eROSITA.
So has that been done on existing information? So you take X-ray information, then you compare it with what you get from optical, for example, and you find some distribution, but also a bias, or I don't know, how does it work out in terms of current observation?
Yeah, of current observations, we have the problem that these survey sizes are really small, right? So we're talking about at most 50 clusters which have measurements in X-ray that are reliable and also in weak lensing that are reliable. And I guess 50 is already an optimistic estimate. So we're really talking about small number statistics at the moment. So what you can actually use then as a tracer are things like RedMapper, right? Taken from the BOSS survey, which is just an algorithm to establish an optical cluster center, but that already gives you an idea of what this miscentring distribution might look like in reality, right? But we clearly need larger surveys to really have statistical hold on that, yeah.
It's a silly question. Tell me what the science is. So I assume that these PDFs are built MCMC samplers. How do you make them so smooth? Is it like a density distribution?
No, I think it's just, well, I mean, not even the sample density is that large, so they just came out like that.
I think these programs can have some smoothing.
Yeah, but I really tried not to use any smoothing at all because that sometimes messes with your, especially with these discontinuous distributions. So I think it's a well-behaved likelihood in the end, which helps.
Any other questions? No, sorry, let's thank Fabian again.
Thanks.